Welcome to this presentation by SU Developments, presented by James Board, Jack Doolan, Lewis Sandry Maddox and Tyler White. This project involved providing the University of Salford with a new hub of entrepreneurship building. We believe this ties in with our brand values, innovation, sustainability, open and free communication and diversity. This is the location of where the building will be built, and these are the elevation drawings for the building.
Hello, my name's Lewis and I'm going to be doing basement technologies. Upon looking at the site plans, we realised that we would need to place the basement walls right down to the bedrock layer at 6 metres due to the high groundwater table, which will cause expansion and contraction within the subsoil, resulting in ground movement. This would straight away be seen as a huge disadvantage for the following walls, which are gravity walls, cantilever retaining walls, crib walls and gabion walls, because the walls require large open excavations which utilise the angle of repose. If we do the calculation for the distance needed to utilise the angle of repose for these walls based off the steepest angle for the part of the site ground conditions, which is clay moist at 45 degrees, we find that we need 6 metres to utilise the angle of repose. This straight away shows that we must eliminate the discussed walls for our basements, as we simply do not have the sufficient space needed around the site to make use of them. Here is a drawing showing which sides of the building this may affect. As you can see, based off the previous drawing, using the angle of repose would mean we would have to dig up the southern walkway, which is an access route to and from the university and also student living quarters. The dumpling method and sheet piling may be seen as alternative solutions to this problem. However, the dumpling method can only achieve a maximum depth of 3 meters, while sheet piling generates high levels of noise and vibration, which would disturb student learning and occupants living within proximity of the site. This is an advantage for the use of contiguous piled walls, secant piled walls and diaphragm walls, as these walls do not require an angle of repose and can be built vertically, which takes up less space. However, we can also eliminate contiguous piled walls from our selection, as the significant disadvantage of these walls is that they cannot retain water from entering the basement, which is key for our basement, as it is required to be a minimum grade 2 waterproof basement in accordance with British standards, as it contains 2 storage rooms and a plant room. We can also eliminate secant piled walls, as they are less cost effective than diaphragm walls and do not guarantee total waterproofing due to the large amount of joints that they contain, which means there will be a higher chance of water ingress into the basement. Whereas diaphragm walls can provide us with the level of water tightness that we need, as we can lay the walls with a lower number of joints, as diaphragm walls can be laid up to 6 meters long, which results in lesser joints than that of a secant piled wall. With the previous research being considered, I will be choosing diaphragm walls as our basement wall choice, as they can be used as a form of foundation to support the superstructure, as a dewatering technique for the ground, and also to form our basement walls. We would use a sodium bentonite slurry instead of a calcium bentonite slurry as trench support, because sodium bentonite can swell up to 18 times its dry mass, whereas calcium bentonite is a non-swelling bentonite. The swelling of the sodium bentonite will prevent water ingress and the collapsing of the trench during excavation. We can eliminate the need for the use of tanking and drained cavities, as our diaphragm walls will be our form of dewatering technique. To achieve the dewatering, our concrete will be waterproof, water stops will be used between joints, and the bentonite sealant tape will be used at the joints between the floor slab and diaphragm walls. We require at least grade 2 waterproofing due to a plant room and storage areas being present in the basement. To achieve this, we will use Cemex Permatite waterproof concrete, which conforms to all waterproof grades, along with a sulfate resistant admixture. This combination enables us to meet the durability and moisture exclusion functional requirements of the basement. Information on the type of water stop to be used can be found in the appendix. We will not need to make use of ground anchors or raking shores, because this would be an unneeded additional cost. However, we have devised a method of construction which combats the occurrence of overturning and the release of overburden pressure in the soil. We will need to construct in a manner that combats potential overturning and bellying out of the walls. We will not take the floor slab the full depth of the basement, as digging too low will cause a release of the overburden pressure that is currently being placed on the soil that occupies the floor slab area of the basement. If this is released, then it can lead to the ground heaving of the soil, which will lead to unsettlement of the diaphragm walls. This will cause the walls to overturn, as shown in the displayed image. To combat this pressure release, we could excavate to 4.3 meters deep and lay a 400mm concrete floor slab on top of a 60mm void former layer, using the same waterproofing methods as we have used for the walls, such as waterproof concrete and internal water stops. By only digging to the stated depth, we allow for settlement of the parts of the diaphragm wall that are below the ground slab, and we eliminate the need to excavate and move excess waste material to nearby dumping sites. Information on the delivery access ramp can be found in the appendix. Widths of diaphragm walls can range from 450mm to 1500mm depending on the loads that they are supporting. Upon searching, there were no regulations which gave guidance on what width we should choose, so we decided to make the wall widths equal to the thickness of the steel frame and cladding above, with an extra 150mm projection either side. This enables us to accommodate and provide sufficient support for the cladding and steel frame superstructure. Here is the section through of our basement, which shows that we have left space at the top of the walls in order to allow for the bolting down of the frame. This is a section through of our floor slab and diaphragm wall joint, which shows the bentonite sealant tape we will install to prevent water ingress through this joint. This is a section through of our floor slab joint, which shows how we will make use of internal water stops to prevent water ingress. It also shows the void former layer we plan to use to combat ground heave. This is a section through of our radon sump pit and its pipework. It is sealed with a bentonite sealant to prevent water ingress. Info for the radon sump can be found in the appendix. Here are the references. Thank you for listening.
Hello, my name is Jack and I'm going to be talking to you about the foundations. When evaluating the site information, we noticed there would be a basement on one half of the building. This area does not require a foundation, as the basement walls will provide the building with suitable support. When evaluating the ground conditions, it was clear that the demolition waste cannot be built on and therefore must be excavated and removed. There is also a water table at 1.2 meters below ground level, which will affect the performance of the sand and the clay. When the sand is compacted, like it will be under the foundation, it is unable to retain water. This will cause the sand over time to wash away and create gaps under the foundation, causing settlement and movement. Although stronger than the sand, clay can swell in volume when it becomes wet. This will cause the effect known as shrink swell, causing potential settlement and movement within the foundation. Bedrock will be a suitable depth to take the foundation to, as this is consolidated rock 6 meters deep from ground level. This can extend hundreds of meters below the ground to provide as much support as possible. One possible option that could be used is a raft foundation. This is a large slab that covers the whole area of the building, useful with poor ground conditions, and can be used as the floor slab. However, this requires long construction time, and the amount of reinforcement can make this an expensive method. Pad foundations transfer the point loads to suitable strata below, useful when constructing a steel frame structure, but will require good ground conditions. This is good when operating on a tight site, but can be more costly the deeper it is required to go. Pile foundation transfer the load of the structure as far down as is required, using driven piles down to the bedrock. They use friction to provide additional support, as they are driven with no excavation and work well when there are high levels of groundwater. The foundation I have chosen is a driven pile foundation. This is because it is a space and money saving process and works well when there are high levels of water in the ground. Also, this is a very suitable method for the steel frame structure that is going to be built. Each pile will be constructed at 2.5 meters apart, which is the required distance between each pile. It will also be driven to a minimum depth of 3 meters, as this is what is required to reach the bedrock after the removal of the demolition waste. Each pile will have a 100mm projection to the sides of the pile caps, in order to spread the weight of the load evenly. Here you can see where the foundation will be required from the red line on the plan drawing. Due to the high water table, it is important that we make sure this foundation is waterproof. Groundwater will alter the pH levels in the concrete, causing the calcium carbonates to dissolve and weaken the concrete. This can also cause freeze-thaw as the water freezes in colder months, causing the concrete to expand and crack. Waterproof concrete will be used to prevent this. We have chosen Cemex Permatite waterproof concrete, as mentioned in basement section also. This will allow our foundation to be more durable and prevent corrosion within the concrete and reinforcements. Driven piles is a simple process that involves driving a steel tube formwork down to the required depth. Steel cage reinforcement is then inserted, followed by the pouring of the concrete. The steel tube can then be removed during the pour of concrete or after. The pile caps, which will be constructed on top of the piles, is then required. Formwork is used for when the concrete is poured, so it can take the shape as is required, but will then be removed when the concrete is set. Steel columns are attached to the pile caps using base plates, which are fixed on top of a layer of grout to provide stability and support for the column. Bolts are held in place within the concrete using two steel plates, which ensure bolts are accurately positioned. Here you can see a section through of the pile foundation. Here is a section through detailing how the steel frame will be joined to the foundation. Thank you for watching this section of the presentation on the foundations.
I'm James Bourne and I'll be doing the structural frame. The type of frame used to construct and support the building is important in many different areas. The frame provides stability for the building, the frame will determine the shape of the building, and the frame resists dead loads, live loads, dynamic loads, and depending on the geographic location can be designed to withstand earthquake loads. The first load that is considered is the vertical load, and that is the dead load. The dead load in a simplified manner is the load that is permanent or static. These loads are mainly associated with the weight of any structural elements and will most probably remain constant for the duration of the building's lifetime. The live load refers to any elements that are considered to be temporary, dynamic or changeable. These elements will include the occupants of the building, furniture and vehicle traffic. All of these elements are not permanent and are subject to change quite frequently. Wind load refers to the movement of air relative to a structure. Wind loads are not really a major concern when it is to do with small, low-rise buildings. According to design buildings where the dead load of a structure is insufficient to resist wind loads, additional structure and fixings may be required. I have made some comparisons of different types of frames for this project and I've decided to compare three very common types: traditional frame, traditional timber, steel frame and concrete frame. These are all very common and the specification and nature of the project will affect the choice of frame used. Concrete as a fluid material in the beginning can be created into almost any shape required, providing very little limitations on design. Reinforced concrete has a high compressive strength compared to other building materials. In other words, concrete offers a good resistance to being pushed together, whereas tensile stress is being pulled apart. Concrete requires less skilled labour for the erection of the frame, and having reinforced concrete can withstand tensile stress reasonably well, again being pulled apart. The maintenance cost of reinforced concrete is very low and the connections are homogeneous with the rest of the structure. Concrete frame has many disadvantages, some being the cost of the forms for reinforced concrete are higher than that of other types of structural frame methods. The tensile strength to compressive ratio in concrete is around 1/10 of its compressive strength. It is also vulnerable to weather changes, as reinforced concrete can be subject to cracking because of the shrinkage and creep that may occur in reinforced concrete structures. Also, aesthetically, it may not be as pleasing. Timber frame construction can be of high quality due to its off-site fabrication and being manufactured in a controlled environment, and it is not affected by elements such as weather. It is a natural material, and generally timber is not a toxic material, and it is safe to handle and does not leak chemical vapors into the building. Timber offers great insulation as the material is a natural insulator, and it allows for more space for insulation, thus minimizing energy costs. The build time for timber is generally very quick, and it is easy to work with. Timber is a very versatile material and can be used in many different ways. It is also lightweight, so therefore easier to install using less complex equipment. Even though timber frames are now the most popular choice amongst social housing, since the Grenfell disaster, the government now has a lot of safety concerns over the risk posed by timber frame blocks. Timber framing requires a lot of maintenance as it can be prone to elements such as rotting, where condensation can occur, and it also requires a lot of fire-resistant treatment. A lot of the construction for the frame will happen off-site, therefore increasing the carbon footprint of the building because of transporting timber to site. Now finally onto steel. Steel framing is very resistant to fires, and steel frames can have a flame retardant coating applied to further increase the fire resistance. Well-built or well-constructed steel frame structures can provide long-term durability and also affordability. Steel can also be considered to be sustainable because of its recyclable compatibilities. Steel also has a great moisture-resistant property. Special coatings can be applied such as hot zinc and extra powder treatments to further increase the moisture resistance, and because of steel's durability, it allows for the design of large, clear-span buildings and also permits for the construction of skyscrapers. Although I mentioned steel has great fire protection properties with added protection from a flame retardant coating, compared to that of concrete it actually has relatively small fire resistance. Although steel elements are incombustible, their strength reduces at high temperatures, making them susceptible to buckling. Steel cannot be moulded into any direction, and it can only be used in forms in which the sections already exist. The maintenance costs associated to steel can be very high, with the need of fireproofing treatment and special treatment to act as a barrier between the steel element and the atmosphere due to it being prone to corrosion. Large variations of steel structures expose the element to excessive tension, which reduces its overall strength. For this project I have decided to choose steel frame. Compared to that of timber, it is considerably less expensive, again using the word sustainability, and as previously mentioned, steel is recyclable and will reduce the carbon footprint of the building. Steel is also more structurally sound than timber, meaning you can build much larger open plan spaces without the need for pillars or load-bearing walls. Compared to that of concrete, although concrete could be used to create complex and imaginative shapes, it takes a lot longer to construct. The speed of construction, the amount of usable space, and the services integration within the building are all factors that need to be considered when constructing a steel frame. Steel bracing is commonly used amongst structures which are prone to lateral loads such as seismic pressure. There are many different types of bracing methods that can be used, such as horizontal bracing, vertical bracing, cross bracing, and eccentric bracing. This type of steel frame, however, restricts the floor space and obstructs the location of internal windows and doors. A rigid frame resists lateral loads. The frame is designed to transmit beam end movements and shear forces into the columns without bracing systems to resist lateral loads. A rigid frame consists of columns and girders joined by moment-resistant connections, and rigid frames may be connected in such a way that it will not limit or restrict the amount of usable floor space. For this project, a rigid frame will be suitable. It is generally used quite a lot for buildings up to 4 stories, but can go much higher if required. Depending on the architect's intentions, a rigid frame can be architecturally exposed, and the multiple beam to column connections provided stiffness and bending resistance in order to resist horizontal loads. This detail shows the different elements involved in the steel frame chosen. The structural frame chosen is a rigid steel frame, but will consist of a stub column made from reinforced concrete. The steel frame will sit on a pile cap foundation, as this is generally the type of foundation used for steel frame buildings. The pile cap will be at suitable depth on a bearing stratum. The concrete foundation will support the stub column, which has the column holding down the bolts cast into it. According to OAS.org, the height of the stub column is such that the column base is located at the desired elevation. Since the steel frame buildings are quite generally a light structure compared to that of other structures, especially concrete, the size of the footing is determined by the size of the anchor required to prevent uplift from wind loads.
Hi, my name's Tyler and I'll be covering the cladding part of this assignment. Cladding in modern architecture can be defined as a protective covering shielding the outside of the building while also potentially adding extra quality and value to the external design of the building. Therefore, is subject to potential weather damage from the natural elements requiring the build's veneers to act like skins undergoing mechanical, chemical, thermal and hydrometric stress. Consequently, cladding is subject to functional requirements that ensure the scope of the design is appropriate to the determination of potential risks and meet all the building regulations, which include approved documents A, B, C and E. According to the Building Envelope Authority, wind has the greatest potential to cause damage to a cladding, and due to the 4-storey building being located in the UK, weather can be quite unpredictable. I reviewed the average wind speed and direction of the wind in Salford to get an idea of which part of the building is typically vulnerable to imposed wind loads. This is usually the responsibility of the structural engineer, but this is sometimes overlooked, leading to potential weather damage. According to Meteo Blue, the average wind direction in Salford is southwest and can get up to 38 miles per hour. This arises the need for extra care towards the selection of cladding. Moving on to thermal considerations, there was no U value requirement mentioned in the brief, and as one of our company values is sustainability, our choice of cladding will be high in thermal retention to reduce the amount of energy consumption that may otherwise be necessary to power heat appliances. According to Kingspan, for non-domestic buildings, the U value must meet 0.22. Other factors to consider are low embodied energy production, which is important to the success of the design to meet company values, a youthful modern external design which will ensure it suits the student-aimed appearance that ties in with the other buildings on campus, and also a vandal-proof glazing as the building is located on a university campus which makes it subject to possible damage from antisocial behaviour. I chose 4 cladding systems: curtain wall, sandwich panel, rain screen and patent glazing in order to get a comprehensive understanding of the selections available before selecting an appropriate system and its materials. After considering all the possible systems, I decided to remove sandwich panel cladding from my selection as it's very similar to rain screen systems. Curtain wall systems typically used for large-scale buildings consist of an aluminium frame with infill panels, usually referred to as glazing. The system has the ability to have good quality control as you can have them factory pre-made and delivered on site, but this can prove to be costly due to transportation costs. Maintenance can also be costly due to the sealants needing replacements frequently and the embodied energy to be high due to the range of materials needed in this system. A rain screen cladding system usually consists of insulated panels with a non-permeable glazing for good water resistance. The panel is also positioned with a ventilation profile in between the insulation and panel, so any rain that does penetrate the panel doesn't reach the internal part of the building. Rain screen can also be cheap with the right materials, making it a versatile system. Modern paint and glazing systems are typically aluminium bars forming a frame which provides support along 2 edges for infill panels, usually double or single glazed glass. But due to the amount of glass used in this system, the amount of embodied energy will be significant and the internal temperatures could negatively be affected, acting almost like a greenhouse. And glare could also become an issue due to the building being an active workplace. So the system that will be used for SU developments is a Stowe Ventec ventilated rain screen cladding. I chose this system because it was the most suitable for the design specification in hand, as it provides an efficient level of insulation with the use of mineral fibre to obtain the required U value of 0.22. It features a Metrion Trespa glazing, which is a high pressure compact laminate made up of natural fibres and thermosetting resins, making it blast and vandal proof. Trespa also allowed for more versatility in the final render, which will also be treated to avoid decolorization from weathering. This system also features a 96% recycled glass fibre mesh reinforcement to increase its resistance to high wind loads, and is suitable to be fixed onto almost any substrate with the use of flexible wall bracket fixings to also accommodate site discrepancies. The elevation drawings with a north and south facing view of the building demonstrate the youthful design of a familiar gradient finish and colour scheme, taking design inspiration from other university buildings around the world to ensure the design ties in with the rest of the buildings on campus. The first detail demonstrates how the system will be attached to the steel with the wall bracket fixed to the insulation, followed by a breathable weather barrier, ventilation profile, glass reinforced mesh and Trespa glazing. Detail also features the fire stops that will be installed in between each floor to prevent the spread of a fire. The next 2 details demonstrate the section through of the roof and ground level. The roof wasn't covered in our work, so the single line indicates the position instead. Where the building meets the ground and roof, vents are present to allow the passage of excess wind to flow into for better control. That's everything on cladding for this part of the assignment. Thank you.